What's up, guys? My name's Michael and welcome to my YouTube channel. And this is actually the second time I'm recording this because I did not turn on the microphone and I didn't set it up correctly. So this is my second time recording this. Anyway, we're going to talk about not binary search trees. We're going to talk about search trees today. And we are going to talk about binary search trees, but we're going to talk about search trees today. And before you continue this video, please hit the like button and hit the subscribe button because I really need some motivation. I need some motivation because it takes a lot of time and energy to talk about data structures. All right, so please hit the subscribe button and hit the like button down below. And we're gonna talk about search trees and what kind of search trees we're gonna talk about. We're gonna talk about binary search trees, AVL trees, Splay trees, red block trees, all these good trees. The difference between a search tree and a regular tree is that search trees, they typically allow you to search things more efficiently in trees, and these are really good because you could use these to implement maps and dictionaries and stuff. So what are binary search trees? They're trees that allow you to search things very efficiently, and you could use these to implement ordered maps and ordered dictionaries. Recall that a dictionary is basically a map, except you could have multiple different values for the same key value. So you could have two correspond to 5 and two correspond to 10 or whatever. And that's what the good thing about dictionaries. That's what dictionaries are. You could use an iterator that allows you, this is just a review, to go through a structure. These are all the standard functions for a map. Finds the entry, puts the value into entry if it doesn't exist. If it does exist, it replaces it. This is just for a map. Erases the key value for whatever key it is. Erase P removes the position for whatever you're at based on the iterator, because you're passing an iterator, and if the iterator points to a position in the map, so it removes it. Begin returns the iterator to the first entry, and returns an iterator to the last last value, just one after the last value. Okay. Yeah, you could use key value. You could use these. Okay. Let's go to the next one. So good thing about binary search trees is that they allow you to search things efficiently. And what exactly is a binary search tree? Well, it's basically a tree that has anything less than it goes less than the current node that you're at is on the left side, and everything greater than the current node you're at is on the right side. That's basically what a binary search tree is. These allow you to efficiently get a value in a binary search tree, because if you are at, like, let's say you want to find the value 43, well, 43 is less than 44, right? So everything on the right tree you could just disregard on the right side of your tree. It's like, we know 43 is less than 44, so I don't have to search through the right side because I know everything on the right is greater than. So I don't need to search through on the right side, and that eliminates all these searches that I have to find, and these comparisons that I need to find. I don't have to compare to 88, 65, because I know all these guys are greater than 44, and I could just compare on the left side, and I could we know 43 is greater than 17, so I could compare on the right side now, and I could just forget everything on the left side because I know everything on the left is less than 17, and then I could just keep going, and because we know 43 is greater than 32, I could go on the right side, but there's nothing on the right side, so that means that I don't have the value 43 in this binary search tree. So that's a good thing about binary search trees, is that you could have the keys as you're storing for each node, and then you could put them in a binary search tree, and your keys, you could eliminate the reasons to you could eliminate a lot of comparisons. That's what they're saying. So I basically talked about the algorithm already. Where is it? This is the algorithm. If you don't have the node, you just return it, right? Not if you don't have the node. This is saying if there's no children, then just return it, because if you're on this side, like, there's no children here. If the 80 has no children, right? So you have to return. But if you're less than the key of what you're at, you go to the left side. Recursively call this tree on the left side. So that means you go to the left and search it. If you're greater than the key that you're at, then you recursively call on the right side, and then you return whatever key you are at. So that's basically how it works. I basically explained that. The height, basically the time complexity, is O of H plus S, I think, right here. For find all, for if you use a binary search tree for a dictionary. For the cost per node in a regular map, I guess. It's O of 1, and it runs in O of h, where h is the height of the tree. Yada yada yada. So you guys might be wondering, how do I insert an item in a binary search tree? Well, there's one way to do it. Okay, so one, you could create a method called insert at external. External, remember, means that it has no node, no children, no children. Insert at external means it has no children, right? So we are assuming that this V is the external node you want to insert it at, right? So if I pull up, let's say I pull up a binary search tree, right? Let's say 4 to 15. All right, let's say this is 14. Let's say this is 21. Okay. I need more values. Okay, let's say this is 20, and then let's say this is I don't know, 25. Okay, 25. Okay. Basically, insert external means we're gonna find the new element, not new element. We're gonna find the external node V, right? The external node V. External node means it has no children, right? We're gonna find the node V that has no children, and then we're gonna create a new node that has the data value E, and we're gonna insert it at that node V. So what does that mean? So here, if I want to insert the element 13, right? Insert at external, right? Add the node 14, right? I want to find the node 14 and insert 13 at it. External means it has no children, right? Because 14 here, it has no children. So I want to insert at external means I'm going to insert the element 13 at the node 14, which has no children, right? So what does that do? It's going to basically create a new node that has the element 13, and then we're going to try to insert it right here. Now, how do we do that? Think about it. How are we going to do that? Well, this method, insert at external, because we know it's external, we could just insert it at that position. Okay. Because we know 14 has no nodes, right? It has no children. Because we know 14 has no children before right here, inserting it would not be that difficult, because all you have to do is find that position where you're inserting it at, and then just create your new node, your 13, right? And then just check if your value is less than the node that has no children. You put it on the left side, which 13 it is. Create a new node, and then have the left side point to it. Or you could create a new node and if you figure out it's greater than 14, well, you could, like, let's say I wanted to insert well, I can't insert 15 because 15 is the same as 15. But let's say you wanted something greater than 14, but it wasn't greater than your root, right? Then you would insert it at that position on the right side. So basically, insert at external, you find the node and you insert it at the left and right side. Well, because that's basically what they're doing here. Well, here, so here they're basically inserting it at the position. Well, now you're saying, how do I insert it though? What if I just want to insert a node at any node, right? At any key. Well, one way to do it is you have to find the node. If it's internal, here's the node tree insert, right? We're going to keep going to the left side if it has children. Once it has no children, we insert it at that position, okay? This is basically just going to keep finding the node that has no children, and then once you find it, you insert it at it. So here, we're trying to find 14, right? So basically, it's going to keep going to the left side because we know it's less than 15, right? We know 14 is less than 15. The key that we're trying to find, 14 is less than 15. So we're going to keep going to the left side or the right side, doesn't matter. So if whatever we're at is internal, that means it has children, then we're going to keep going to the left side. Okay? That's what it says. You could have another if statement, like if it's less than it, then go to the left side, or if it's greater than it, go to the right side, right? But here, this is just a simple insert. Once we're done recursively going to the left side, right? That means we already found our node that has no children. Because if we kept going left, and we went left, okay, and keep going left, or now finally we're at 14. All right, let's say there were way more nodes here, okay, but let's say there were way more nodes here, right? And so you could imagine, I'm going left and then left and left, and then finally, okay, I'm at 14. Now what do? I'm going to call the method insert at external WKX. Okay, and what does that do? That created a new node with the element E, and it inserted the node at the external node V. Okay, so that basically inserted the node 13 on the left side, because this function insert at external inserts the node, creates a new node, and then has the left side or the right side point to it. So yeah, that's basically what this is doing. The algorithm traces a path from T's root to an external node. Remember, external node means it has no children. Internal node means it has children. Okay? So this function actually allowed us to find the node with the specific key, right? Until it found the one that has no children. And then it inserted at it. Okay? So this algorithm traced the path from T's root to an external node, which is expanded to a new internal node, accommodating the new entry. An example is this binary search tree. So it kept going right, left. Well, in this case, in this case, they also went right and left. That's just another if statement here, but they didn't include that. So let's say they wanted to insert at 80, right? So they just went, okay, 80 is greater than 44, so they went right. Well, 80 is less than 88, so they went left. Well, 80 is greater than 65, so they go right. Well, 80 is less than 82, so we go left. So 80 is greater than 76. So he's like, okay, go right. And then now we want to insert the element 78. So we went left, and we figured out because 80 has no children, based on these holes here, these square boxes represent null, right? These square boxes represent null. Then we finally inserted 78 at the left side of 80. Okay? So this basically just keeps searching for your node that has no children and the node that is like less than the current node based on going left or right, right? And then they finally inserted 78 at it. So that's how this insertion works, okay? Okay, so now we're going to talk about how to remove something from a binary search tree, and that's a little harder. Here, I'll give you an example why. Let's say I have 12, and then let's say I have 10 here, and then I have 14 here. Let me just give you a complete picture on why removing is way harder. 18, let's say I have 17, and let's say I have 21, and here I have 20, 22 or 23. I don't know. I just want to make sure that you guys get the picture. Here's the reason why removing is harder. You don't want to have holes in your tree. Let's say I want to remove 18. Oh, okay, you might think, let's say I just delete 18. Here's the problem. If I just delete 18, what am I going to do with this? What is 17 going to be at? Where's 21 going to be at? All right. What about 20? What about 25? You don't want to have a hole in this tree. Removing is harder than it looks. Because if you have children, you have problems. All right. But let's say I wanted to remove 10. Well, 10 is easy because it has no children. I could literally just keep going to the left side or the right side until I find 10. And once I find 10, I realize it has no children, and I could just be like, okay, set the left side to null. And that deletes it. So the problem about removing is that you don't want to create holes in your tree, right? If you have children at that position, it gets really complicated. So here's the reason. So I went over why you don't want to have children. So if you remove above external, what does that mean? Moving above external means that you remove an external V and its parent. External means it has no children, right? You remove an external node V and its parent, and you replace V's parent with V's siblings. This basically is saying that I will keep. I will take. So given an external node 10, right? I'm going to remove the 10. Let's say right here. I'm going to remove the 10 here, and the parent, which is 12, and I'm going to replace the parent with 10 sibling, which is 14. So here they're basically saying remove above external v means I'm going to remove 10 and 12, which I kind of don't understand why they're doing that, because they could just remove 10. But remove above external, we're not just removing the node 10, right? We're going to remove 10 and 12, then replace 10 sibling, which is 14, to be replace v's parent, v's siblings. Yeah. Remove the external node v and its parent, and then replace v's parent with v's siblings. So then now 14 is going to be right here. Let me just delete this. So now 14 is going to be on the left side of 15. So that's what remove above external does. Basically, they're going to have a function called remove above external, and it removes an external v and its parent, which I showed you, and replace v's parent with its siblings. An error occurs if this is not external. Given this operation, you can begin your implementation of the operation erase of the map by calling the tree search with your key value, and then call it on the root to find a node of t storing an entry with the key value equal to k, right? So because we have this remove above external, we can now try to find our node by calling a tree search function. We could create a function called tree search that finds a k and storing the entry with the key. If the tree search returns an external node, meaning that our value k that we're trying to find, the key that the node with the value key that we're trying to find has no children, then there's no entry with key in map of m, and an error occurs if it is signal. So if it has children, then an error occurs, because that means that there's an entry with the key in our map. If there is no children, like currently it is, then nothing. That means there's no key with it, and then you could basically remove it, right? Like if it has no children, that means you can remove it, because that means there's no entry with the key k in our map. That's what they're saying here. Otherwise, if it returns an internal node w, which means that it has children, that the key node that we're trying to find with the specific key has children, right? Let's say I'm going to go back into paint. Let's say we try to find 12, right? If 12 had children, has an internal node w, right? So let's say 12 had a key, right? I don't know, 1 or whatever. And then we loop through our whole tree, try to find the key 1, okay? And then we figured out, okay, well, it returned the node 12, but we realized 12 has children. Then we realized 12 has children, and we're trying to remove 12, right? Then we have two cases. If one of the children of the node that we're removing is an external node, which means it has no children, we simply remove w and z by means of operation remove above external. And this restructures the tree by replacing w with the sibling of z. Remove both w and z from t. This is basically saying that if the node that we're trying to remove, let's say 12, it has one node that has no children, we call it z, then you could call up remove above external, and that would remove I'm gonna delete 14 just to make sure it has this example, okay? So actually I shouldn't have deleted 14. Okay, basically I want to create 14 Let's say I have 13 here also. So they're basically saying, okay, let's say I want to remove 12, right? And I realize one of the nodes of 12 has no children. Like, because here, 10 has no children. Well, because of this, I could just call remove above external. Remember what I said about remove above external? Remove above external basically deletes the node 10 and the node 12 and replaces the node with the sibling of it. The node 10 with the sibling of it. And removing both W and Z from T. So that removes 12 and 10 and then replaces this 14, which has children, right? We know this has children, to be the parent of it. So if that's the case, we could just remove those two, okay? That's what they're saying here. If instead it returns an internal node, then W stores an entry which we want to remove. We have two cases. If one of the children W is an external node, say Z, external node means it has no children, we simply remove W and Z by means of an operation remove above external on T. This operation restructures T by replacing W with the sibling of Z, removing both W and Z from T. So that was one of the cases we were talking about, okay? But if both of the children of W are internal nodes, that makes it way more complicated. Internal nodes means it has children. If both of 12 had children, which I'm going to draw this. Let's say both of them had children. Let's say this had, a 9. Okay, 9. Okay, 9, 13. This is really hard to draw. Let's say 11. I don't know. 11's less than 14. Okay, 11, 18. I don't know. Okay, so basically we're trying to remove 12, right? Well, 12, both of these children have children. Like, both of the children of 12 have children. See, 10 has children, 9 and 13. 14 has children, 11 and 18. That's going to be very hard. Okay? Because we would have holes in T. So, here's what we're going to do. Find the first internal node, Y, that follows W in an order traversal. So they're going to keep going to the left and the right children until we find a node, first internal Y, node Y. Internal node Y means it has children, right? We're going to find the first node that has children using in order traversal. We're going to move the entry of Y into W, and this action has effect of removing the formal entry stored at W. And then we're going to remove the nodes X and Y T by calling remove above external. And this replaces Y with X sibling and removes both Y and X from T. Okay, so I'm going to explain this, but I need to get a drink. So in this case, we are trying to find the first internal Y that follows W in an in-order traversal of T. What does that mean? We're trying to find the first node Y that follows W. So because let's say I'm deleting 12, right? And the children, both children of W, are internal nodes. That means they have children. Well, you cannot simply remove W from T. So like, let's say I want to remove 12. And both of these have children. Like, 10 have children, 14 also have children. I can't just remove 12. Since this would just create a hole. So what am I going to do? I need to find the first node, internal node W. Internal node Y. That follows W in an order traversal of T. So, first internal node Y, what is that? First internal node Y. Internal node means it has children. So, I want to find the first node that has children. First node Y that follows W in an order traversal. Okay? So I'm going to find the first internal node Y. So the first internal node Y that has children the first internal node y. Okay, so that follows w. Okay, so currently our w is 12, and 12 has both children. 10 has children. 14 has children, right? There's no children there's no children of 12 that have no children, right? Because both of the children of our node 12 are internal nodes. That means they have children. So we're gonna find the first internal node y, which basically means the first node y that has children after w in order traversal. So now y is the leftmost internal node in the right subtree of w. So what does that mean? We're going to go to the right side of 14 of our node of our w. So our w currently is 12, right? So we're trying to find then first an internal node y. Internal node y. So we're going to find the first node y that has no children on the right side. So how do you do that? You have to keep going to the right side, the right child of w, and then from there you have to go to the left children. Okay? Using in order traversal. So which node following on the right side of w, which is 14, right? Which node has children? The first internal node that has children. Okay? Well, none of them. But let's say there was, okay? Let's say 11 had another child, let's say, I don't know. 16, okay? 16. I can't move this, but let's imagine this has 16, okay? This is 16, okay? So, we're going to go to the right child, right? The right side of the RW, and we're trying to find the first internal y. And then we're going to internal y on the left side of the right child. So that's 11, right? Because 11 has children. It has a 16 on the right side of 11. It's not 18 because the 18 has no children. 18 is external, right? So we're trying to... So let's say we found 11. So this is our y. This is now our y, okay? So now what are we going to do? We move the entry of y into w. The entry of y into w. Okay, so we're going to move 11 into w. So now this is going to have 11, I guess. Okay? We remove the nodes x and y from T by calling remove above external x. Okay? So we're going to remove the nodes x and y from T by calling remove above external. And this replaces y with x as a sibling and remove both x and y from T. So what was x? X is the left child of y. Right? The left child x of y is the external node that immediately follows w. Right? So x is we're going to remove nodes x and y from T by calling remove above external. X is the left child of y, which is the external node that immediately follows w. The left child of y, well, is nothing because there's no external node, right? But in this case, it could be 16. So that's going to replace y with x's siblings and remove. So we're going to call it remove above external x. And I'm guessing that's going to delete the value of 11. And it's going to replace 16 to be the left child of 14. Because I'm guessing that was our x. Because we didn't have any other child on the left side. Right? So that would remove both x and y from T. So that's basically what it did. So now 12 is gone. Now 12 has the value 11. 16 replaced our 11. 16 is now on the left side of 14. And everything's still in order. Okay? So yeah, that was that. As with the searching and insertion, this removal algorithm traverses a path from the root to an external node, possibly removing an entry between two nodes of this path, and then performs a remove above external operation at that external node. The position-based variant of a removal is the same, except that we can skip the initial step of invoking tree search to locate the node containing the key. So here they're going to explain it again. So we're trying to remove the binary search tree where the entry to remove key 32 is stored at the node W with an external node child. So they're trying to remove 32, right? But there's an external node child, which is this square box. And what are they going to do? They're going to basically delete 32 and replace the left side, which is 28, as the node of it. That's what they're doing. Here, it's the same thing that we said. Removing the binary tree where the entry to remove is stored at the node W, whose children are both internal. So we're going to go to it. So we're going to try to remove 76. Both of the children of... wait, let me see. Whose children are both internal. So yeah, so both of these children have nodes. Okay? So what are they going to do? They're going to get the... So yeah, so because the children of 76, 80 has an internal node, is an internal node, right? It has children, 78. Both the nodes of 76 have children. Both the children of 76 have children, right? Except for this null, left side. But left side is it's null. There's no children on left side. But both the nodes of 76 have children, and we're removing 76. So what do? They're going to find 80, and they're going to call the remove at external of 76, and because there's no node on the left side, they delete it. And then they're going to have 80 replace it, which is right here. 80 replaces the value of 76. Like all the nodes on the right side of 80 is now replaced for the values of 76, right? So like right here. And the value of 65 now becomes a value of 76, which is what we saw, which is what I showed you previously. Did I accidentally go up? Let me see. Yeah. Yeah. So that's what happened. The performance of the binary search tree. Insertion, removal, and search are all similar. O of 1 at each node visited. Worst case is the number of nodes visited is proportional to the height. Thus, in a map with the binary search tree T, find, insert, and erase runs in O of H time, where H is the height of T. Thus, a binary search tree T is an efficient implementation of a map and entries only if the height of T is small. In that case, T has height of O log of n plus 1. Okay. So here's the performance O of 1 for size and empty. Find, insert, erase depends on the height of the tree, O of H. Okay. The average is generated from a random series of insertions and removals of a key that has expected to have height log of n. Such a statement requires careful mathematical language to precisely define what we mean by a random series of insertion and removals. As sophisticated probability theory is proved, thus is justification beyond the scope of this book. Nevertheless, keep in mind the poor worst case performance they take care of using the standard binary tree in applications, where updates are not random. There are, after all, applications where it's essential to have a map with fast worst case search and restore. Okay, so let's talk about how to implement the C++ implementation of binary search tree. So basically, we're going to create a class called search tree. Here's the difference. It's going to be a dictionary. So it's not the same thing as a map, because now we could have multiple copies of the same key. So 2 could have 8, the value 8, and 2 could have the value 16, right? But for simplicity, we didn't implement the find all function. So here they're just saying that we're using templates, parameters, and we're just keeping everything simple. We have a key and a value. Alright, so here's type def just means... Type def here just means another name for K is just key. Type def another V means another name for V is value. Okay. So here they have, this is the constructor that initializes the key and value. These are just accessors that returns the key and the value. This just sets the key and the value. Okay. Then we have K key and KV value, which is just the key and a value. And this is the class for entry. Okay. This is the whole class for entry. It's not the search tree yet. This is just for every single entry has a key and a value. All right. In our tree. Or we're trying to implement a dictionary technically, so yeah. A dictionary tree. Let's just call it dictionary tree, whatever. So now we're gonna represent the main part of the search tree. So we need to define accessors for the entry, the key, value, and the iterator, because you also want to go through the whole tree. We need public members, so we declare two different local types, binary tree and T position, which represent a binary tree and position within the binary tree. We also wanted to have a number of local utility functions that help in finding, inserting, and erasing entries, and the number of entries in the binary tree. Okay, so we still have the key and value in our search tree and iterator. Okay. Key value, this is just a way to rewrite. K just means have key and value is just V. Okay, that's just type name is just an alias for the name. Whenever you see key, it means K. Okay, or K means key. Okay, and value, whenever you see value, it means V. Okay. Okay, so we have a search tree. Return size, empty, checks empty. Find, insert. Find returns the iterator, which is a position at specific key. Insert, it's a method that inserts a key and a value. Okay. Erase, erases the key. Erase, erases whatever at that position. P, it passes an iterator. Iterator begin, iterator end. Okay. Okay, so those are all our public methods, but we also have protected. We're going to have a separate binary tree. It was a linked binary tree. This is a type def, by the way. So that means that type def means that the binary, whenever you see binary tree, it means binary tree. Okay, that's what they're saying here. And position, whenever you see T posis, it means position. Root is going to return the root of the tree. Find ER finds the utility. Wait, what? Finder. Oh, my bad. Finder returns the a position tree position at the key and the value. Wait, find utility. I don't know what that means. Okay, inserter. Okay, insert at the key value. What? Returns the T position. Erase utility. Restructure. Okay, I don't know what these are. But basically, we're going to have a binary search tree, which is our instance variable. And we're going to have a number of entries. And, yeah. We're going to have a binary search tree as an instance variable. The search tree has a binary search tree. And, yeah, it also has the number of elements in it. That's what our search tree is going to have. And it has all these methods. Okay, now we're going to define an iterator. It just returns an instance variable for the position in the list. Has the constructor that initializes the iterator. We're overloading the star so that we could use star for our iterator, which returns the data at the thing, at the entry. We're doing this just so we could use the iterator. Whenever we use the iterator, we could use it like a pointer. So we could use star. So that means we could get the data that this is pointing to. Yeah, it's the same thing here. These are the same thing. Whatever. Okay, equals returns if the iterator is the same. Plus just in order successor. And we use find class tree search tree, which gives our class search tree access to all the methods of iterator. Add the private instance variables, my bad. Okay, so here represents the definition of iterator's increment operator, which advances the iterator from a given position of the tree to its in-order successor. Only internal nodes are visited since external nodes do not contain entries. If the node V is the right child, the inner node tree, okay, what? It's the leftmost internal node of this right subtree. Otherwise, V must be the largest key in the key traverse subtree of some node W. Okay, to find W, we walk up to the tree using successors. Okay. We continue moving upwards. This is no longer true. The parent is node V that we employ. Okay, this is just basically just saying that how to traverse it. Okay, so when we're searching the tree, if it has no children, no, if it has children, right? Okay, wait, okay. This is ridiculous. Okay, I'll explain it. The plus is just incrementing an iterator, right? So if I have 15, 14, and 20, 21. Actually, 19. Let's do 19. 19, 21. Okay, so we're going to get the right position at our, where we're at, okay? If it's, so let's say I start at 15, okay? Which is the root, okay? I want to keep going to the right, okay? I want to go through all my nodes, okay? So I'm going to go to the right side, because why would I go to the left? 14 is the value before 15, right? When you plus an iterator, you're going to the right next node, right? So I'm going to go to the right. So that's this. Okay, this is the right. 20 is the right. Is it internal? That means does it have children? Yes, it does. So what does that mean? While it's internal, I am basically going to go to the left. While it has children, I'm going to go left. Alright, so finally, I'm at 19. So that means if I went to the left, and I always went to the left. Why do I go to the left? Because the left is the last value that's greater than our current node, 15. That basically is the next node after 15. Alright, in a traversal. Alright, so the next value of 15 is 19. And then I return 19. Alright, that's the plus, because I have the next value of 15 in order is 19. Okay, we go left. Let's say there is no internal node, as in, which I don't know how that's possible, but that internal node means there's no children, okay? So let's say there's no internal node, that means it's external. If it's external, which means that 20 has no children on the right side. Alright, let's say 20 on the right side has no children, okay? Well, W is going to equal the V dot parent. What's V? V to the right, so currently I'm at 15, right? V to the right. V's parent has no parent, so it's null, okay? If V is equal. What? Okay, well, I didn't have a good example. So basically what they're doing is they're going to get the parent, and they're going to check if my current node that I'm at is equal to the right node. The parent's right child. Then I'm going to set my node to equal to the parent, and then I'm going to return it. Okay, so I'm going to get the parent and move on to the right side. That's what they're saying here. All right. So yeah. That's basically how to go to the next node in a search tree. There's a lot of the rightmost trees and okay. I want to go over this before I'm going to get... So there's a problem that occurs if the iterator points to the rightmost node of the tree. Then the above function would loop until you arrive at the node which has no parent. The right node of the tree has no successor. The iterator would return to the value's end. So there's a better way to achieve the desired behavior. You add a special sentinel node called your tree called the super root, which is created when the initial tree is constructed. The root of the binary tree, which we call the virtual root, is made the left child of the super root. And then we define the end to be an iterator that returns the position of the super root. Observe that if we attempt to increment the iterator that points to the right node of the tree, the function would move to the right chain until it reaches the virtual root, and then stop at its parent, the super root, since the virtual root is its left child. Therefore, it returns an iterator pointing to the super root, which is evaluated to the end. This is exactly the behavior we desire. To implement this strategy, we define the constructor to create the super root. Then we also define a function root, which returns the super root's position. That is the left child of the super root. Okay, so you create the super root, and basically it's saying that this stops the problem of going back to the root's value or something. So you create the super root, and then you get the virtual root. Okay, these are the two constructors. And then you define the functions begin and end, which returns the first node according to the in-order traversal, which is the leftmost internal node, and then the end returns the position of the super root. So that's what they do here. Position of the super root. Alright, now they're going to represent the implementations of the class functions for finding and inserting or removing. You begin by presenting the functions find. They have their own utility function and an auxiliary function, the helper, that helps them do this. This utility function is based on the algorithm given in the code fragment. This is based on the keys. Okay, so if it's external, what does that mean? External means that it has no children. Then we return the node. Okay, all right. Otherwise, we check the key to the left side. If it's less than the current key we're at, then we recursively go to the left. If it's greater than the current key we're at, recursively go to the right. Otherwise, we return V. Okay, that's how we do this. Okay. So now, because we have the auxiliary function or utility function, whatever, we have our iterator find K. Alright, and we're going to get the position of the root. If it's internal, that means it has children. Then we return iterator V. Okay? That means we found it. Otherwise, we return end. Okay? So here they're calling their finder function that finds the key. If that position has no nodes, then we return iterator to it. Otherwise, we return end. Okay. Okay. Here are the insertion functions that are shown below. The inserted utility does all the work. It searches for the key. If it finds it, it continues the search until it reaches a node that has no children, name external node. Recall that we allow duplicate keys, then we create a node and copy the information to the node and then update the entry count. Insertion function simply invokes the insertion utility and converts the resulting node into an iterator. The resulting position. Alright, so then we find the position using the finder. While it's internal, what does that mean? While it's internal means it has children, then we use finder on the right, alright? And then we expand external. We add a new external node, then we set each keys and values, add one more entry, and return V, alright? Yeah, that's basically what it's doing. Expand external just adds a new value to it. New entry to it. Yeah, that's basically it. Set the values, find it, go to the right, yeah. Finally, we represent the remove functions. We simply implement the approach set in here. If the node has an external node, we set the W to point to the child. Otherwise, we let W be the leftmost external node on the right subtree. We let U be the parent, and we copy the entry into the contents V. In all cases, we then remove the external node and the parent using the binary functions remove above external. So this, we already talked about this, so I'll explain it again. My throat is hurting me right now. Alright, so we're going to go here. If the current position we're at, if the left side is external, that means it has no children. Then we go to the left. We set W to the left, right? Otherwise, that means it has, if the left side has children, then we go to the right side, check if it has children, okay? If it doesn't have children, okay? External means it doesn't have children, okay? Then we set to the right side, alright? Else, we get the node on the right. We keep going to the left until we figure out it has no children. Once we do that, we get the position we're at and get the parent of it, the one that has no children, alright? Then we set the keys and the values to equal to the values of the parent, and then we subtract the node, the number of nodes, then we remove above external on W, okay? Erase is the same thing as it just calls the search tree finder. Which finds the root that we're at, and then we call it eraser V. Eraser V removes the position of it. Okay, and then erase is just the erase entry at P. We're going to do that, and we call that, okay. When updating the node and the entry, we explicitly change only the key and value using set and key and set value. You might wonder what else is there to change in the chat. Represent data structures that are based on modifying the entry class. It is important that only the key and value data are altered when copying nodes for those structures. Our implementations are focused on the main elements of the binary search tree implementation. There are more a few things that we could have been included. It's a straightforward exercise to implement the dictionary operation find all, which would be worthwhile to implement the decrement operator. Alright. Oh, time to go through advanced trees. So now we're going to talk about AVL trees. So in the previous section we discussed that what should be an efficient map data structure. But the worst case performance achieved for the various operations is linear time, which is no better than the performance of list and array based map implementations. Well, we're going to describe a simple way of correcting this problem to achieve logarithm time for fundamental map operations. So let's talk about AVL tree. So what is an AVL tree? Well, an AVL tree is basically a rule to a binary tree definition that maintains a logarithmic height for a tree. So the rule consists of following a height balance property, which characterizes the structure of a binary search tree in terms of the heights of the internal nodes. That the height of the V in the tree is the length of the longest path from V to a height external node. So this is going to be the height balance tree for every internal node V of T. The height of the children of V differs by at most 1. So any binary search tree T that satisfies the height balance property is said to be an AVL tree, named after the initials of its inventors. Here's an example shown below. The keys of the entries are shown as the nodes, and the heights of the nodes are shown next to the nodes. Okay, so here the height of 4 is 4 because, well, 1, 2... Oh, wait, it's the 1, 2, 3, 4. Wait, 1, 2, 3, yeah. 1, 2, 2, 3, 4. Okay, so yeah, so the height of the tree is the so basically an AVL tree allows you to is basically a good tree that rebalances the height of a binary search tree. And the reason for that is that if your binary search tree, if all the nodes are on the right side or the left side, it's not balanced, then finding the node is very hard because it depends on the height of the tree. So for a binary, the height balance property for every internal node V of T, the heights of the children differ by at most 1. So here, 17 is the internal node. The height of 17 and 44 differ by at most 1, right? 1. 50 is a tree, no, it's a internal node. The height between 50 and 78 differ by 1. Alright, so you can't have a node that's like an internal node that is not balanced, like all the way on the right side. So that's what an AVL tree is. In median consequence of the height balance property is that a subtree of an AVL tree is itself an AVL tree. The height balance property has also the important consequence of keeping the height small, as shown in the following proposition. The height of an AVL tree storing n entries is log n. So instead of trying to find an upper bound on the height of the AVL tree directly, it turns out to be easier to work on the inverse problem of finding a lower bound on the minimum number of internal nodes, n of h, of the AVL tree with height h. We show that n of h grows at least exponentially. From this, it is an easy step to derive that the height of an AVL tree storing n entries is log of n. So this is just a proof of it. I could read it, but first let me just plug in my computer's charger because I'm about to lose battery. Okay. So to start with, notice that n of 1 is equal to 1 and n of 2 is equal to 2 because the AVL tree of height 1 must at least have one internal node and an AVL tree of height 2 must have at least two internal nodes. Now for height greater than 3 or equal to 3, an AVL tree with height h and the minimum number of nodes is such that both of its subtrees are AVL trees with a minimum number of nodes of one with height h minus 1 and the other one h minus 2. So taking the root into account, we have the formula related to n of h to n of h minus 1 and n of h minus 2 for a height of greater than or equal to 3. So n of h is equal to 1 plus n of h minus 1 plus n of h minus 2. At this point, the reader, familiar with the properties of Fibonacci progressions, already see that n of h is a function exponential in h. For the rest of the readers, we will proceed with our reasoning. Formula implies that n of h is a strictly increasing function of h. Thus, we know that n of h minus 1 is greater than n of h minus 2. N of h minus 2. So replacing n of h minus 1 with n of h minus 2 in the formula and dropping the 1, we get n of h is greater than 2 times n minus h minus 2. So the formula indicates that n of h at least doubles each time h increases by 2, which means that n of h grows exponentially. To show that this fact in a formal way, we apply the formula repeatedly yielding the following results. I accidentally pressed the right button. So n of h is greater than 2 times n of h minus 2, which is greater than 4 times n of h minus 4, and you keep going. So that is n of h is greater than 2 to the I times n of h minus 2i for any integer I such that h minus 2i is greater than or equal to 1. Since we already know the values of n of 1 and n of 2, we pick I so that n minus 2i is equal to either 1 or 2. That is, we pick I is equal to h over 2, the upper limit minus 1. Okay, so by substituting the above value of I in the formula, we obtain for h is greater than or equal to 3. Taking logarithms of both sides of the formula, we obtain this, from which we get that. Okay, so we get log of 2h to log of nh greater than h over 2 minus 1. So we get h is less than 2 log nh plus 2, so which implies that an AVL tree storing nh entries has height at most 2 log n plus 2. And by the final analysis, we realize that it runs log of n time, where n is the number of entries in the map. Of course, we still have to show how to maintain the height balance tree after insertion or removal. Okay, let's talk about update operations for inserting. Wow, this takes a lot of energy. So the insertion and deletion for AVL trees are similar to those of binary trees, but they have to do additional things like reordering them, making sure that the height of an AVL tree is the internal nodes of each one is at most 1, right? Because we're trying to make sure the AVL tree is balanced. So an insertion in the AVL tree begins as an insert operation described in the section for a simple binary search tree. Recall that this operation always inserts a new node at a node W in T that was previously an external node, and it makes W become an internal node with operation insert at external. That is, it adds 2 external nodes chosen to W. This action may violate the height tree balance. However, for some nodes, it increases their height by 1. In particular, node W, and possibly some of these ancestors, increasing their heights by 1. Therefore, let us describe how to restructure T to restore its height balance. So given a binary tree T, we say that an internal node V is balanced if the absolute value of the difference between the heights of the children of V is at most 1, and we say that it is unbalanced otherwise. Thus, the height balance property characterizing AVL trees is equivalent to saying that every internal node is balanced. Suppose that T satisfies the height balance property, and hence is an AVL tree. Prior to our inserting the new entry, as we have mentioned before, after performing the operation insert at external on T, heights of some nodes of T, including W, increase. All such nodes are on the path of T from W to the root of T. These are the only nodes of T that may have just become unbalanced. Of course, if this happens, then T is no longer an AVL tree. Hence, we need a mechanism to fix the unbalance that we have just created. Okay. So wait, that whole paragraph just told us that we have to fix unbalance. Okay, so here they insert at each tree, right, and they're trying to balance this. So they're trying to get the 62 to go to become a balanced tree. They want this tree to become balanced, so what they're going to do is they're going to take the 62 and move it up, and they're going to put 78, move it down, and then that would fix this balancing problem for this height of having one node and then two non-children, right? Having one node and then one non-node, right? The example here is key 54 of the tree. After adding a new node, the nodes storing keys 78 become unbalanced. So they're going to try to restore the height property. We show the heights next to them, and we identify the nodes participating in tri-node restructuring. So we restore the balance of the nodes in the binary search tree by a simple search and repair. In particular, let Z be the first node we encounter in the algorithm going up from W towards the root of T, such that Z is unbalanced. So also let Y be denote the child of Z with higher height. Finally, let X be the child of W with Y with higher height. Be a tie and node X be the ancestor of W. Also note that X is a grandchild of Z and could be equal to W since Z becomes unbalanced. There's an insertion in the subtree at the child height, at child Y. Height of Y is 2 greater than sibling. So now we need to rebalance it. We do this tri-node restructuring function called restructure. A tri-node restructuring temporarily renames the nodes X, Y, and Z as A, B, and C. Just that A precedes B, B precedes C in order traversal. So there are 4 ways of mapping X, Y, and Z to A, B, and C, which are unified in one case by relabeling. The tri-node restructuring then replaces Z with the node B and makes the children of this node A and C, makes the children A and C be the 4 previous children of X, Y, and Z, maintaining the in-order relationships of nodes T. So for restructuring a tree, they're basically, this is really way too complicated. They're letting A, B be the left side of the tree and then replace it. This is too complicated. So let me just tell you guys what it's like, okay? A simple explanation for simple reordering of trees. So let's say I have 13, 15, but then I have 16, right? But then let's say 16. I did something stupid, right? It's not ordered. It's 18, then it's 20. Well, what do they basically want you to do? To reorder this, they basically want you to move... well, you can't really reorder this, but... here in this case, they kind of want you to move... They want to move this so that it's ordered like 18... Like all these 16, 18, 20, right? 18 would be like that, and then 16, and then 20. So in order to do that, we're going to have to move this 16, 18, and 20. We gotta delete, we gotta reorder them, right? So do that. Basically, to make this height good, we're gonna have to take 16 and just move it. And then make the 18 become the node of this. And then have the 16 be the left child of this 18. And then have the 20 be the right child of this 18. Like that. Whoops. Oh, wait, okay. I'll just take out this. Just reorder. 20. And that's basically it. That's basically what we're trying to do, to reorder. Okay? So that's what all this jargon means. So to do that, the modifications caused by restructuring operations, often called rotation. Because of the geometric way we can visualize the way it changes t. So if b is equal to y, the trinode restructure model is called single rotation, for it can be visualized as rotating y over z. Otherwise, if b is equal to x, the trinode restructuring operation is called a double rotation, for it could be visualized as first rotating y over x and then over z. Some computer researchers treat these two operations as separate models, each with two symmetric types. As you have chosen, however, to unify these four types in a single trinode restructuring operation, no matter how much we view it, the trinode restructuring method modifies the parent-child O1 onto the nodes T, while preserving the in-order traversal. So in addition to the order-preserving property, it changes the heights of the T and it restores balance. Although recall that we execute the restructure because the grandparent of X is unbalanced. Moreover, this is unbalanced due to the children of X not having too large of a tree on the height of Y. As a result, we move up the tall child, pushing down the short child of Z. Thus, by performing restructure X, all the nodes in subtree now are rerouted for the node B and they're balanced. Thus, we perform the height balance tree property locally at the nodes X, Y, and Z. In addition, since after performing the new entry insertion, the subtree rooted at B replaces the old former tree rooted at Z, which was taller by 1 unit. All the answers to Z that are now formally unbalanced become balanced. And that's what it's called. Therefore, this restructure also restores the height balance property globally. So yeah, this is what it's doing. So let's say you have a tree like this. They're going to have A equals Z, B equals Y, C equals X. And they're going to have to make this B become the middle. And A is on the left and C is on the right. Single rotation. Here's, let's say they're all on the left. All these nodes are on the left side. Well, we're going to have to move them. So we're going to have B become the middle. And A on the left side and C on the right. Let's say we want a double rotation. Let's say we have A, C, and B. And we know that these heights are different by a lot. Because T1 has a different height than T2, right? See, it's way bigger. So we want T1 to have the same height as T0. So what do? We're going to have to move B, the left side of B now has to become the middle of this child, and then we have A become the left of B, and C become the right of B. Now let's say we want a double rotation. Well, we want to move because of the height of T2. We have to move B to become the center, and then have A become left of B, and C become the right. So that's how this is the huge gist of it. Okay, so removing, as with the case of insertion, we have to begin the implementation of race on the tree by using the algorithm to perform this operation on a regular binary search tree. The additional difficulty in using this is that we may violate the height balance property. In particular, removing a internal node with the operation remove above external and elevating one of its children onto its place. There may be an unbalanced node in T on the path from the parent W of the previously removed node to the left root of T. In fact, there can be one such unbalanced node at most. So yeah, so let's say we have a node that's unbalanced right here, 17, 44, 62. Okay, so one has a height, this has a height of 1, and this has a height of 2. Well, we want to balance these because this has a height of 4. So we want to move 44, which this has a height of 1, this has a height of 1. And this has a height of 0, and this has a height of 1. So we want to make all these have a height of 1, or at least be balanced. So we're going to move this to the center of here, make 62 become the new node, new root, and then move 78 to become the top left, so then all these are balanced. So as using insertion, restructuring restore balance on the tree T, in particular let Z be the first unbalanced node encountered going up from W toward the root of T. Also let Y be the node child of Z with larger height, and X be the child of Y as follows. If X is taller than Y, else we have the same height. And then X be the child of Y on the same side of Y. Also, X be the right child of Y. Okay, restores the height balance locally. Okay, unfortunately, the trinode restructuring may reduce the height of the subtree root by 1, which may cause an ancestor B to become unbalanced. So after rebalancing Z, we continue walking up T, looking for unbalanced nodes. If we find another, we perform a restructure operation to restore its balance and continue marching up T, looking for more all the way to the root. Since the height of T is log of n, where n is the number of entries, Trinomial restructurings are sufficient to restoring the height balance property. Okay. Here's the performance of AVL trees. We summarize the analysis of the performance of AVL trees as follows. We have insertion, find, insert, erase, plus their siblings have O of 1 time, since the height of t is log of n. Operations take O of log n time. In the table 10.2, we summarize the performance of a map implemented with an AVL tree. Size and empties log O of 1. Find, insert, and erase is log of n. Okay, so that's, yeah. This illustrates the running time, searching. The time performance is O of 1, broken into a down phase, which typically involves searching, and an up phase, which typically involves updating the height. Okay. Alright guys, so let's talk about the C++ implementation of AVL tree. So let us now turn to implementation details analysis of using an AVL tree with n internal nodes to implement a dictionary order of n entries. So we know that insertion and removal algorithms require that we perform the reconstruction and determine differences between the height. And regarding reconstructions, we now need to make sure that the underlying implementation of a binary search tree includes the method restructure, which performs the restructure operation. Excuse me. I need to see the reconstruction operation can be performed at O of 1 time if t is implemented with the linked structure. We assume that the search tree class includes this function. Regarding the height information, we have chosen to store the height of each internal node v explicit in each node. Alternatively, we could have stored the balance factor of v at v, which is defined at the height of the left child of v minus the height of the right child of v. Thus, the balance factor is always between -1, 0, or 1, except during insertion or removal, when it becomes temporarily equal to -2 or 2. So, during the execution of an insertion or removal, the heights and balance factors of O log of n are affected can be maintained in log of n time. Okay, so in order to store the height information, we derive a subclass called AVL entry from the standard entry class we saw earlier. It is templated with the basic entry type, from which it inherits the key and value members. It defines a member variable h of t, which stores the height of the subtree rooted at the associated node. It provides the member functions for accessing and setting this value, and these functions are protected so the user cannot access them. So, we have the height, private. This is just type def, just to make sure we rename key and value to make it easier for us. Okay. We have the height h that returns the height, and we could set the height for each entry. And then we have a constructor that initializes the height to 0, and then the whole entry, and then we make it a friend class of AVL tree to allow every AVL tree access to it. So we represent this class definition of AVL tree, and this class is derived from the class search tree, but using our enhanced AVL tree entry in order to maintain height information for the nodes of the tree. The class defines a number of type defs, shortcuts for referring to entities such as keys, values, and tree positions. The class declares all the standard dictionary member functions at the end. It also defines a number of protected utility functions which are used to maintain the AVL tree properties. So here, this AVL tree class inherited the search tree. Okay, and then these type def is just an easier way to write AVL entry. Whenever we see AVL entry with the E, we're just going to write, we replace it with this, right? So this, whenever we could just use this to represent that whenever we write it. That's what the type def is for. So that's what they do. They type def a bunch of these stuff. Okay, so now once we type def all of that, it's easier to write things out. Now we have the AVL tree constructor. You have the iterator insert, KV, inserts a position. We have erase, that throws non-existent element. We have erase iterator P. We have the height, set height. Check if it's balanced. This gets the tallest grandchildren, and then we have the function rebalance. Next, in the code fragment, we represent the constructor and the height utility function. The constructor simply invokes the constructor for the binary search tree and creates a tree with no entities. The function height returns the height of the node by extracting the height information from AVL entry. We employ the condensed function notation as introduced here. So this just creates an empty tree. This returns the height. If the height is If the position has no children, is external, right? No children, then we return 0. Otherwise, we return the height of the tree. Let's see. Represent a few utility functions needed to maintain the tree's balance. The function is setHeight sets the height information for a node as more than the maximum of the height of its two children. The function isBalance determines whether a node satisfies the AVL balance condition by checking that the height difference between its children is at most 1. Finally, the function tallGrandchild determines the tallest grandchild of a node. Recall that this procedure is needed by the removal operation to determine the node to which the restructuring operation will be applied. So we have setHeight. This just sets the height of left and right. So we get the height of the left, get the height of the right. Sets the height to be the maximum of the left and right. Wow. Okay. Balance just isBalance checks. We subtract the height of the left and the right, and then we check if it's greater than or equal to -1 and it's less than or equal to 1. Then that means it's balanced. If it's not, because if the height's different by 2 or more, 1 or more, -2 or a 2, that means something's wrong. Tall grandchildren, get the position of left and right. We check the heights. Is the left side greater than or equal to the right side? If it is, then we check is the left side height greater than or equal to the right side height. Isn't this the same thing? What? Okay. So this got the height of the left. This is the tree on the left. This is the tree on the right. We get the height on the left, and we compare it to if it's equal to the height on the right. If it is, then we get the grandchildren of the height on this left, or the height of the left side, get its height again, and get the height on the right side to check if it's greater than or equal to. If it is, we return the left. Otherwise, we return the right. If the height was in the first place never greater than or equal to the right side, we check if the right side is greater than or equal to the left. This is so many checking. Okay. Then we return the right. Otherwise, we return the left. Some utility functions used for maintaining the balance in the AVL tree. Next, we represent the principal function for rebalancing the AVL tree after an insertion or removal. The procedure starts at the node V affected by the operation. It then walks up the tree to the root level. On visiting each node Z, it updates Z's height information and checks whether Z is balanced. If not, it finds Z's tallest grandchildren and apply the restructuring operation to this node, since heights may have changed as well as a result. It updates the height information for Z's children and itself. So here they have rebalance. Get the position that we're currently at. We check if it's not the root. While it's not the root, we get the parent. Set the height of it. Check is it balanced. Okay. If it's not balanced, we get the height of the tallest grandchildren, and then we reconstruct it, and then we set the height of left and right, and then the height of the node that we're at. Okay. Yeah, I guess this would work. I would want to go over this code, but I don't feel like it. I mean, you could, guys, try drawing this out using your own binary search tree and see if this would work. Alright, let's see. We represent the functions for inserting and erasing keys. Each invokes the associated utility function, insert, erase, or respectively from the base class. So if you want to insert something, get the position, create an inserter. Inserts in the tree, set the height, rebalance, return the iterator, the position of it that you're at. Erase, get the position of the find and base tree, right? Check if the position is equal to n. If it's not found, we throw a non-existent element exception. Otherwise, we get the position. We're gonna get the position and remove it, and then we rebalance if needed. Okay, so if it's found in the base tree, if it's not found, we throw an exception. Otherwise, we remove it, and then we rebalance it at that position that we removed it from. Alright, so now we're going to talk about how to implement We're going to talk about splay trees. Okay, so another way you can implement the fundamental map operations is use a balanced search tree structure known as a splay tree. It's different from the other balanced search trees because for a splay tree, it doesn't use any explicit rules to enforce its balance. Instead, it applies a more move to root operation called splaying after every access in order to keep the search tree balanced in an amortized sense. The splaying operation is performed at the bottommost X reached during an insertion, deletion, or a search. The surprising thing about splaying is that it allows us to guarantee an amortized running time for insertion, deletion, and searches. This is logarithmic. The structure of a splay tree is simply a binary search tree, T. In fact, there are no additional heights, balance, or color labels that we associate with the nodes of this tree. So given an internal node of X of binary search tree T, we splay it by moving X to the root of T through a sequence of restructuring. The particular restructuring we perform are important, for it is not sufficient to move X to the root of T by just any sequence of restructuring. The specific operation we perform to move X up depends upon the relative positions of X, its parent Y, and if it exists, X's grandparent Z. There are three cases that we consider. Zigzag. The node X and the parent are both left children or right children. So we replace Z by X and making Y the child of X. So here we have Z, Y, X. We replace Z with X, right? And make Y the child of Z. Y the child of Z. Replace Z by X. Replace Y the child of Z. In order to maintain the in-order relationship of the node. So A is before, B is after. So, wait, I don't understand what's going on. Okay, so ZYX, let me just zoom in. This is before. We have ZYX, alright, so these are unbalanced, right? Well, actually, well, it is balanced, wait. Okay, so what they're going to do is they're going to replace Z by X, so then this is going to be X. This 30 is going to have 30 here, and then we're going to reorder, make Y the child of X, and Z the child of Y, so that maintains the in-order relationship. So then that changes this to become that. So that Z is now on the bottom. Y is the child, parent of Z, and Z is the parent of Y. That's because these two are not in order, so now we make this the bottom on the left, so then this is more balanced, I guess. This is another symmetric configuration where X and Y are left children. I kind of don't understand why this is the how this is more balanced. Okay, so the node X and this parent are both left children and right children. I kind of like the other one better, but I don't know. So zigzag, one of the Y, X and Y is a left child and the other one is a right child. So if it's like this, you replace Z by X and make X have Y and Z as its children. So X now becomes the top of this, and then Y and Z become the children. So that's what this, so this Z was now the children of X, if you have something like that. Now that was zigzag, right? Okay, so the first one was a zigzag, the second one was also a zigzag. We're going to have zig. X does not have a grandparent, and we are not considering X's grandparent for some reason. In this case, we rotate X over Y and making X's children to be the node Y and one of X's former children W to be in order to maintain the in-order relationship. So X does not have a grandparent, or we have not considered X's grandparent for some reason. So this doesn't have a grandparent, right? So we're going to rotate X over Y and make X's children to be the node Y and one of X's former children W in order to maintain the in-order relationship. So X is now the head, and then we have to make Y the children, and then W is the other child. Okay, so we perform a zigzag or a zigzag. A zigzag or a zigzag. Okay, so the other one was a zigzag. Let's see. This one was a zigzag. Okay, so this was a zigzag, and then this one was a zigzag. This is a zig. Okay. It's another systematic configuration where X and Y are left children. So we perform a zigzag or zigzag when X has a grandparent, And we perform a zig when x has a parent but not a grandparent. The splaying step consists of repeating these restructuring at x until x becomes a root of t. So note this is not the same as a sequence of rotations which brings x to the root. Examples of splaying nodes we have right here. Okay, so they're going to splay this. So, because these have different heights, right? And then it's going to be like that. Okay, so they're going to reorder 14, 13, and 15, so it becomes this. Do they splay again? Yeah, they splay it again. So now these nodes are going to splay this. So, splaying the node, starting at 14 with a zigzag, and after zigzag, next step is zig-zig. So that becomes, so this becomes 12, 10, 12, okay, there was a zig-zag. Okay, so now they're doing a zig-zag. So now because we have 10, 11, 12, 14, that's going to zig-zag to this. Yeah. Oh, that's pretty cool. So then now, because we zig-zag, it becomes more balanced. So 10, 11, 12, 14 is going to rebalance to 11, 12, 14 on the left to the right side, right? So now that's more balanced. I think we're going to zig-zag again. Okay, so then this is now going to be that. So this from 8, 10, 14, from all the way on the right, it's going to be 8, 10, 14 from left increasing. So we have that. We're going to zig-zag again. Zig-zag, and then we zig-zag again. Okay, so when to splay. The rules are that dictate when splaying is performed as follows. When searching for a key, if the key is found at the node x, we splay x, else we splay the parent of the x. A parent of the external node, so the parent of the node that has no children, at which the search terminates unsuccessfully. For example, if you splay the figures of 10.16 and 10.17, you would be performed by searching successfully for keys 14 and unsuccessfully keys 14.5. Yeah. So when inserting the key k, we splay the newly created internal node where k gets inserted. For example, the splaying of 10.3 would be performed if 14 was a newly inserted key, which shows the splaying. Okay, so we splay the parent, which splays. Okay, so if you have inserted 12, inserted 4. Okay, so then they're gonna splay the. They're gonna zigzag. Yeah, they're gonna zigzag this. If it's greater. So then, wait, do they zigzag? Oh, they don't even tell you. Okay, whatever. So they zigzag this. So now 12 is 1 is 12, 1, 2. Then they inserted a 3, and it become. Then they're going to make it the node, the head node, zigzag again, to make it like that. They add 4. That's fine. That becomes the zig. Wait, what? Now it's all in one. Why would you do this? I thought you were trying to balance it. Okay, now it's all in one position like this. So this is a sequence of insertion. Okay, so the first one is an initial tree. You insert it. Here they splay it, right? After inserting 3, they splay it again. After inserting 4, they splay it again. But then these are all in one line. Isn't that what we're trying to prevent? I don't know. I'm guessing they're just showing how to splay. After deleting a key k, we splay the parent of the node w that gets removed. That is, w is either the node of k or one of its descendants. An example of splaying as a following deletion is this. Wait, hold up. Excuse me. Okay, so when deleting k, okay, so we have this. We splay the parent of the node that gets removed. Okay, so what are they trying to delete? V? The node going that gets removed. That is, W is either the node storing K or one of its descendants. What are they deleting? Deleting V? Is this? Well, this is null, right? Okay, so they delete this V, yeah. Then you have 3, 4, 6. And they're gonna splay this. Oh, and then it becomes 3, 4, 6 this way. Okay, so they splay this. Zigzag, I think. Zigzag. Okay, and now it becomes that. Then they're gonna zigzag. 4, 6, 7 is gonna get zigzag, so we have 4, 6, 7 like that. Okay. Delete 8 from the node by removing the key of the rightmost internal node from V to the R in the left subtree, deleting V, and splaying the parent U of V. Splaying in U starts with a zigzag. After zigzag, next time is a zig, and then a zig. Okay, that makes sense. Okay, so this was a zig. Here to here was a zig. Okay, not a zigzag. It was zig. Okay. Yeah, that was it. The analysis of splaying after zigzag or zigzag, that the depth of x decreases by 2. After a zig, the depth decreases by 1. Thus, if x has a depth d, splaying z consists of a sequence of a d over 2 zigzags or zigzags plus 1 final zig if d is odd. Since a simple zigzag, or zig affects a constant number of nodes, it can be done over one time. Thus, splaying a node x in a binary search tree t takes time O of d, where t is the depth of x in t. In other words, the time for performing a splaying step for node x is asymptotically the same as the time needed just to reach the node in a top-down search for the root of t. Worst case time, in the worst case time, the overall running time of a search, insertion, or deletion in a splay tree of a height h is O of h, since the node we splay might be the deepest node in the tree. Moreover, it is impossible for h to be as large as n, as shown in the figure 10.18. Thus, from a worst case point of view, we splay a tree. A splay tree is not as an attractive data structure. Okay, in case of a worst case scenario, a splay tree performs well in an amortized sense. That is, in a sequence of intermixed searches, insertions, and deletions. Each operation takes on average logarithmic time. Perform the amortized analysis of splay trees using a counting method. Okay, so in our analysis, we denote the time for performing a search, insertion, or deletion is proportional to the time needed for associated splaying. Let us consider only splaying time. Let t be the splay tree of n keys. Let v be the root of t. We define the size n of v is the number of nodes in the subtree rooted at v. Note that this definition implies that the size of an internal node is one more than the sum of the size of its two children. We find the rank of the node v as a logarithmic in base 2 of the size of v, that is, r of v is equal to log n of v. Clearly, the root of t has a maximum size 2n plus 1, and maximum rank log of 2n plus 1. With each external node of size 1, we have rank 1 and 0. We use cyberdollars to pay for the work we perform in displaying a node. We assume that 1 cyberdollar pays for a zig, while 2 cyberdollars pay for a zigzag or zigzag. Hence, the cost of displaying a node at depth d is d cyberdollars. We keep a virtual account of the cyberdollars at each internal node of t. Note that the account exists only for a purpose of amortized analysis and does not need to be included in the data structure implementing the splay tree. In accounting analysis of splaying, before you perform a splaying, we pay a certain number of cyberdollars. We distinguish 3 cases, and if the payment is equal to the splaying work, then we use it all to pay for the splaying. If the payment is greater than the splaying work, we deposit the excess in the accounts of several nodes. If the payment is less than the splaying work, we make withdrawals from the accounts of nodes to cover the deficiency. We show that the payment of O of log n of cyberdollars per operation is sufficient to keep the balance working, and to ensure that each node keeps a non-negative account balance. So an account variant for splaying, we use a scheme in which transfers are made between the accounts of the nodes to ensure that there will always be enough cyberdollars to withdraw to paying for splaying work when needed. In order to use the account method to perform analysis of splaying, we maintain the variant before and after splaying. Each node v of t has r of v cyberdollars in its account. Note that the invariant is financially sound since it does not require us to make a preliminary deposit to endow a tree with 0 keys. Let r of t be the sum of all the ranks of the nodes. To preserve the invariant after splaying, we make an account equal to the splaying work plus the total change in r of t. We perform a zigzag, a zigzag, a zigzag operation displaying a tree called substep. When we denote the rank of a node v before and after it's displaying a subset of rv as r prime v. The following proposition gives us the upper bound of the change of rt by a subset. We use the limits in our analysis of the root tree. Oh my gosh. Oh. Okay. Yeah, this is just about a bunch of math. I don't feel like reading this. Okay. Well, you guys can pause the video and read all of this. This is just... I don't feel like doing this. Okay. Yeah, this is way too much math for me. Alright, let's talk about 2 for trees. Alright guys, we're going to talk about multi-way search trees. So recall that multi-way search trees are defined so that each internal node can have many children. So in this section, we're going to describe how multi-search trees can be used as search trees. So multi-way trees can be used as search trees. Recall that the entries that we store in a search tree are pairs of the form kx, where k is a key and x is a value with the key. However, we do not discuss how to perform the updates in a multi-search tree now, since the details for updating methods depend on additional properties that we want to maintain for multi-way search trees. So what is a multi-way search tree? So let V be the node of a ordered tree. We say V is a D node if V has D children. We define a multi-way search tree to be an ordered tree T that has the following properties, which are illustrated here. Each internal node of T has at least 2 children. That is, each internal node is a D node such that D is greater than or equal to 2. Each internal D node V of T with children V1 up to VD stores an ordered set of D minus 1 key entries. Okay. D minus 1 key entries, K1, KX1 up to D, KD minus 1. Okay, so this is just saying that the keys are less than each other. Yeah, these are just saying the keys are less than each other. This is just saying that they have at least 2 children. Like each node that has children has at least 2 children. And we'll define the initial key to have negative infinity and the last key to have positive infinity for each entry kx at each node in the subtree of the V root, rooted at VI. I equals 1 up to D. We have that ki minus 1 is less than or equal to I, which is less than or equal to ky. Okay, so this is just saying that each one is less than or equal to each other. And the first key is negative infinity, the last key is positive infinity. So if we think of the set of keys stored in V as in including the special functions, no, not functions, the special fiction keys, negative infinity and positive infinity, then a key stored in the subtree of T rooted at A, child node VI must be in between 2 keys stored at V. This simple viewpoint gives rise to the rule that a D node stores D minus 1 regular keys, and it also forms the basis of the algorithms for searching in a multi-way search tree. So by the above definition, the external nodes of a multi-way search tree do not store any entries and serve as only placeholders, as has been our convention with binary search trees. Hence, a binary search tree can be viewed as a special case of a multi-way search tree, where each internal node stores 1 entry and has 2 children. In addition, each of the external nodes can be null, and we make simplifying assumption here that they are actually nodes that don't store anything. Okay, so this is just saying that this is just clarifying that the keys are in between. The first key is negative infinity, the last key is positive infinity, to help you store things, and that the external nodes are just as placeholders, and they don't store anything. So like the nodes, the ones that have no children, they just placeholders. They don't store anything. Yeah. So I'm guessing this is a multi-way search tree. So they have more than 3 multiple children. Is that what they're saying? I guess they do, yeah. So this has 3. So as you can see, these are all null. The external nodes point to null. So the ones that have no children have null children, right? And here you could search through whatever key you want, and there's multiple I don't know, there's multiple entries. Each one's less than each other, right? I think that's what they said. Whether internal nodes of a multi-way search tree has 2 children or many, however, there is an interesting relationship between the number of entries and the number of external nodes. An n-entry multi-way search tree has n plus 1 external nodes. We leave the justification of this proposition as an exercise. Searching in a multi-way tree, given a multi-way search tree T, we note that searching for an entity with key K is simple. We perform a search by tracing a path starting at the root. And you compare each key, okay? If it's the key, the search is finished, okay? So otherwise we continue the search in the VI of V, the child of it, such that each key is less than each other. If you reach the external node, then we know that there's no entry with the key in it. Okay, so this is just saying that to traverse through the tree, you have to trace the path down starting at the root. And you have to see if it has children or not. And if it does, then you just keep going. Okay, so there's data structures to represent multi-way search trees. We discussed a linked list data structure for representing a general tree. This representation can be used for multi-way search trees as well. In fact, in using a general tree to implement a multi-way search tree, the only additional information we need is to store each node in a set of keys, entries, associated with that node. That is, we want to store with V a reference to some collection that stores the entries for V. So recall that when we use a binary search tree to represent an ordered map M, we simply store a reference to a single entry at each internal node. In using a multi-way search tree T to represent M, we must store a reference to the ordered set of entries associated with V at each internal node of V. This reasoning may at first seem like circular reasoning, but since we need a representation of an ordered map to represent an ordered map, we can avoid any circular arguments, however, by using a bootstrapping technique, where we use a previous, less advanced solution to create a new and more advanced solution. In this case, bootstrapping consists of representing the ordered set associated with each internal node using a map structure that we have previously constructed. In addition, we already have a way of implementing ordered maps. We could just realize a multi-way search tree by using a tree and storing each map for each node of T. Okay, so this is just saying that we're going to use a map to store every single entry, I'm guessing. The reference to a single entry at each internal node, yeah. So that's all they're saying. They're going to use they're going to use a bootstrapping technique, which is use a less advanced solution to do it. And here, what they're going to do is they're going to have a map structure that representing the ordered set associated with each node using a map structure. Okay, so yeah, that's what they're doing. That's what this paragraph whole thing was about. Let's see what's next. So the map they're going to store each node is using a secondary data structure because we need to support a bigger primary data structure. So you're going to have a map stored at the node V of T as M of V. That's a map. Entries stored in the map will allow us to find each child node to move to the next one during a search operation, specifically for each node V of T, with children V1 and entries K1, X1 up to KD-1 and XD-1. So they store the map in this in the map MV, the entries of that. As an entry to KI, XI, VI of a map has KI and value XI, VI. Okay, so the entry this has a map for the map has a key, and then it has its own value, X1 and VU1. So are these each individual maps? No, okay, this whole thing is a map, and then they're gonna have each entries, like this is the key, and these are each entries for inside the map. I wonder what X21 and I know V1 is a value, but what's X1? I'm kind of curious what that is. They don't say. Okay, whatever. With the realization of the multi-way search tree above preceding a D node V while searching for an entry of T with a KK, key K can be done by performing a search operation to find the entry KI, XI, VI in MV with the smallest key greater than or equal to K. So they distinguish two cases. If the for whatever key you're on is less than the K of I, then continue the search by processing the child. Okay. Note that if the special key positive infinity is returned, then the K is greater than all the keys stored at the node V. So then you continue searching the processing child of VD. Okay. Otherwise, the search is done completely, and then you just terminate. So consider this. Oh, whoops. So consider the space required for the above realization of T of n entries. Using any of the common realizations of an ordered map for the secondary structures of the nodes of T, the overall space requirement for T is O of n. Consider next the time spent answering a search in T. Time spent at a D node V of T during a search depends on how we realize the secondary data structure M of V. If M of V is realized with a sorted array, we can process it in log of D time. If the map is realized using an unsorted list, then it takes O of D time. D max represents the maximum number of nodes in a children of any node of T. Let H represent the height of T. The search time is either HD or H times log of D max. Depending on the search specific implementation of the second data structure at the node T map MV, if D max is constant, then the running time for performing a search is O of H, irrespective of the implementation of the secondary structures. The primary efficiency goal for a multi-way search tree is to keep the height as small as possible. That is, we want h to be a logarithmic function of n, the total number of entries stored in the map. A tree with a logarithmic height is known as a balanced search tree. Okay, so multi-way search tree keys. Okay, so 2-4 is a tree, and is the 2-4, which we sometimes call the 2-4 tree or 2-3-4 tree. Data structure achieved as well. Okay, so every internal node has at most 4 children. Depth, probably all external nodes have the same depth. Okay, so that makes sense. So all these have the same depth between the height, each difference between the height, so that makes more sense. I'm kind of curious on how do they implement this? What was X? And we assume the external nodes are empty, and for the sake of simplicity, we describe assertion update methods, assuming that external nodes are real nodes, although this later requirement is not strictly needed. Okay, so they're just saying that all the external nodes here, right? All these are null, okay? So the ones that have no children, they actually point to null. That's what they're saying. Enforcing the size property keeps the trees in the multi-way search tree simple. It also gives the internal alternate name 2-3 tree, since it implies that each internal node in the tree has 2, 3, or 4 children. Another implication of this rule is that we could represent the map MV stored at each internal node V using an ordered list of an ordered array and still have an achieve O of 1 time performance for all operations. D max is equal to 4. The depth property, on the other hand, enforces an important bound on the height of 2-4 tree. Okay, so this is just saying that having the depth property makes it more efficient. So making sure that you have the height between here and here is not like greater than 2, I think, or greater than equal to 1. The absolute value of each height. That's what they're saying. Okay. Height of a 2-4 tree storing n entries is log of n. Let h be the height of the tree storing n entries. We justify the proposition by making the claims. 1/2 log n plus 1 is less than or equal to h, and h is less than or equal to log of n plus 1 are true. To justify these claims, use the size property. You could have at most 4 nodes, at most 4 2. Okay, that's the number of external nodes before the h, hence the fourth thing. Okay. You must have at least 2 nodes at a depth of 1. Yes, we know that. At least 2 to 2 at depth of 2. So on, the number of external nodes is 2 to a, at least 2 to the h. In addition, by proposition, the number of external nodes in T is n plus 1. Therefore, we obtain 2 to the h is less than or equal to n plus 1, and n plus 1 is less than or equal to 4 to the h. Taking the logarithm of both sides, we get this. Proposition states that the size and depth properties are sufficient for keeping a multi-way tree balance. Moreover, this proposition implies that performing a search in a 2-4 tree takes O of log n time, and that the specific realization of the secondary structure of the node is not a crucial design choice. Since the maximum number of children, D max, is a constant, we can, for example, use a simple ordered map implementations as arrayless search tree for a secondary data structure. Okay. So let's talk about inserting into a multi-way search tree. Alright, let's talk about updated operations for 2-4 trees. So maintaining the size and depth of trees require an effort for performing insertion and removal of 2-4 trees. We discuss the operation next. So to insert a new entry into the key into a 2-4 tree, you first have to perform a search for the key. Because you want to, because what if the tree already has the key value that you're trying to add to? So assuming that the tree has no entry with the key value, the search terminates unsuccessfully at the external node Z. Let V be the parent of Z. If we insert the new entry into the node V, add a new child W, external node to V on the left side of Z. That is, we add entry K X W to the map MV. Our insertion method preserves the depth property while still adding a new external node at the same time as existing external nodes. Notice I may violate the size property. How indeed, if a node V has previously a 4 node, then it may become a 5 node after violation, which causes the tree to no longer be a 2-4 tree. This type of violation of the size property is called an overflow at the node, and it must be resolved in order to restore the properties of a 2-4 tree. Let V1 up to V5 be the children of V, and let K1 to K4 be the keys stored at V. To remedy the overflow at the node V, we perform split operations as follows. So replace the V with the 2 nodes V prime and VW prime, where V prime is the 3 node with child V1, V2, V3 storing keys K1, K2, and V double prime is a node with children V4, V5 storing key V4. So V is the root of T, create a new node U, else let U be the parent of V. Insert the key K3 into U and make V prime and V double prime children of U. So that if V was a child I of U, then V prime and V double prime become children I and I plus 1 of U respectively. We show a sequence of insertions in 2-4 tree here. So here there's an overflow at the 5 node V, right? Because they're adding a new key, right? A new entry, and there's an overflow. Okay, so then a node split. There's an overflow right here. Okay, the third entry, the third key of V inserted into the parent U of V. So that's the third one. The third key is the parent inserted. So they're gonna move it up, move the key up, and to the parent node, and then node V is replaced with the node VI and double prime. So then now the key for this entry that they moved up, this now becomes 2 nodes, so it has K1 and K2, and this is another entry itself, and then these 2 keys, V prime and V double prime, are now the entries of K3. Here's another instance where they add things. So you have 4, then they add 4, 6, 4, 6, 12, right? So these are three entries in the same map, right? And then now there's 4, and then now there's a problem, right? We're trying to add another one, so there's a 5 now. So what they're doing is they take the middle one of 12 and they move it up, and then now this becomes the parent of these 2 children. So then now when they add something, they add something onto the left child, right? And we got 6. But then boom, when we hit the 5th one, we take the middle one and we move it back up to the parent of the child of the parent node. So then now we have 5, 12, 3, 4, 6, and 15, right? So then now when you add a new child, that puts the new child back up to the parent node, just like right here, and we restructure the tree. Okay, so we have 5, 12, 3, 4, 6, 10, 15. So now when we add the new child, this becomes 6, 8, 10. Okay, so here in this case, they're just adding a new child to the middle key, right? The middle one, which is 6, 8. So 6, 8, 10. Right, that's what they're adding here. From K to L, that's what they added. They just added the 8. So they just, because this isn't going over 5, that's why it doesn't affect anything. Alright, so the sequence insertions of 2-4 tree, initial tree with 1 entry, the insertion of 6, inserting 12. So let's just go back up. So the first entry was nothing. We inserted 6, then we inserted 12, we inserted 15. Right, now, which caused an overflow. Then we split, which caused the creation of a new node. After this, so we split at E. So E had a split. So then they took the middle node and then have that become the parent. Alright, so now it's 4, 6, 12, 15. So now we want to, so then after the split, they insert 3 and then they insert 5. So they insert 3 and 5, and that's still on the left child because, like, you have to make sure the left child's finished before you do that. Then they got 3, 4, 5, 6, and then they're going to have to add they insert another one. Insert 3 and then 5, and then that causes an overflow. So then they split again. Okay, and then push the key of the entry back to the top, and then now we have this 3, 4, 5, 12, 6, 15. Okay, and then split again, and then after the split they insert 10 and then insert 8. 10 and 8. So yeah, that maintains, they insert it in the middle because they're trying to make it order. That's why. Alright, so that was that. Here's analysis of the insertion of a 2-4 tree. Split operations affects a constant number of nodes of the tree. O of 1 entries stored at each node. Thus, it can be implemented to run O of 1 time. As a consequence of the split operation on node V, a new overflow may occur at the parent, U of V. If the overflow occurs, it triggers a split at the node U in turn. Split operation either eliminates the overflow or propagates into a new parent of the current node. Hence, the number of split operations is bounded by the height of the tree, log of n. Therefore, the total time performed is log of n. Okay. Yeah, so that's what they're doing here. I'm not explaining that again. Okay, so let's talk about removal. First, I got to get my charger because my computer is about to die. Let's talk about removal. So let us now consider removing an entry with key K from a 2-4 tree T. We begin with an operation by performing a search for the entry with a K. Then removing such entry from the 2-4 tree can always be reduced to the case where the entry to be removed is stored at the node V, whose children are external nodes. Okay. So for instance, that the entry with key K that we wish to remove is stored in the ith entry KI XI at node Z that has only internal node children. In this case, if we have to swap the entry with the appropriate entry that's stored at the node V with the external children as follows. We find the rightmost children in the internal node and the subtree rooted at the ith child of Z, noting that the children of node V are all external nodes. We swap the entry KI XI at Z with the last entry of V. Once we assume that the entry is removed, is stored at a node V with only external node children, because either it was already at V or we swapped it into V, we simply remove the entry from V and remove the ith external node of V. So removing an external entry, a child from a node V as described above preserves the depth property. Because we already removed an external node from a node V with only external node children. However, in removing such an external node, we may violate the size property of V. Indeed, if V had previously 2 nodes, then it becomes 1 node with no entries after removal. Okay, which is not allowed in the 2-4 tree. This type of violation of property is called an underflow in the node V. To remedy an underflow, we check whether the immediate sibling is a 3-4 node. If we find such a node sibling W, we perform the transfer operation in which we move a child of W to V, a key of W to the parent U of V and W, and a key of U to V. If V has only one sibling, or if both immediate siblings are 2 nodes, then we perform a fusion operation in which we merge V with a sibling, creating a new node, and move a key from the parent, a U of V, to V prime. So this is just saying that if there's an underflow, like when you move a node and there's not enough nodes there. So remember, the nodes were between what was it, 1 to 4, I think, right? The keys, each node had to be between like 1 to 4. If you have the 5th one, they cause a split, right? Well, let's say there's less than 1, right? So that has an underflow, right? You don't want to have one node with no entries after removal, right? So that causes an underflow, so they have to remedy that. And sometimes they have to transfer the siblings between each other. So that's what they're saying. A fusion operation at node may cause an underflow to occur at the parent, which triggers a transfer or fusion. Hence, the number of fusion operations is bounded by the height of the tree, which is log of n. If underflow propagates all the way up to the root, then the root is simply deleted. We show a sequence of the removals from the figure's head. Okay, so let's just see what they're doing here. Okay, so first, we remove 4, causing an underflow. Okay, so here, the first one, there's a node here, right? It was 4. We're trying to remove it. Okay, so 4 is the leftmost child of 5 and 10. 5 and 10, right? So if we remove 4, this is going to cause an underflow, right? Because there's no node here. Okay, we want to have at least one node here, right? With an external thing. So what do they do here? Well, they're going to transfer. Again, transfer an operation. Okay, so they're going to take 5 from the parent and move it down, and then when they're going to push 6, have 6 and move it up to become the parent of it. So then now you have 5, 6, 10. 5 is on the part where 4 was deleted. 6 now is the parent. 6 and 10 are the parents. And then 8 is by itself with, oh yeah, and they removed an entry, by the way. A null entry, by the way. They removed this empty entry. Okay, so they removed that because 6, 8 is supposed to have what? These entries of 2 numbers should only have like three non-entries, right? So they remove one of the external things because now it's by itself, right? So 8, now we have 5, 8, 5, 6, 8, 10, 11, right? That's what we have here now. After we move 6 to become parent and we move the 5 down. So now what happens? Well, after that, they're going to remove 12, which causes an underflow. So they're going to try to remove 12 here. So 12 is the root. So once you remove the 12, it leaves like a hole there. So what they're going to do is they're going to push, I think they're going to cause the external node 11 and move it back up to 12. So once they do that, that fixes the underflow. Okay? So after removing 12, it causes an underflow. A fusion operation occurs. So to fuse it, they took 11 and move it back up to to the 11 now is the node, right? 11 is now the root of the whole tree. But then now we have a problem. We have nothing on the right side, right child of 6 and 10. So what do? We take 10 and we put it back down. So the 10 of the parent node, we have to take that 10 and put it down. So now we have 6, 5, 8, and 10. But here's a problem. We don't want to have a bunch of nodes by itself, right? Because that's just not efficient. So what do? They cause a fusion operation. Okay, they fuse the 8 and the 10 to make sure that it's the same height. They're trying to make these similar to each other on the left side and the right side. You see these have to be similar to each other, right? So they fused 8 and 10. After they move 11 to the root as root, and they move 10, the parent, down. So then they move 10 down, and now they fuse 8 and 10. Okay, so now that 8 and 10 are together. So now what do they do after that? Well, let's just see what they do. So after the fusion operation, they're going to move 13. So when you move 13, there's no need to fuse. There's no need to do anything. Mainly because there's there's no need to do it because, I mean, it still has these children are still the same. I mean, there's no holes and there's nothing, so there's no need to fuse it. Yeah. That's why. Here, I'm guessing is you can't have like 3 children, I guess. Or they have to both be at the same. Oh, no, you can. Wait. I don't know why they fuse 8 and 10, actually. Oh, yeah, to make it balance like to the right side. But here they didn't do it. They didn't fuse 8 and 11. Oh, but because there's the 10 value here. Okay. Okay, yeah. I think I got what they're doing. Okay. Now what are they gonna do? Okay, so now they have 8. They're gonna remove 14. Okay, so they're gonna remove 14, and then that has a problem because now we have a hole on the left side, left child, which causes underflow. Then they're gonna fuse. So they take 15 to push it down. What are they gonna do to? They have 15 to put it down. They take 11 down. Okay, so they have 15 to put it down, right? So to fix the hole on the left child. But then that has a problem, right? Because now we have 8 and 10 are together right on the left side. We want to make a balance. So then now we want to have two entries in the same entry on the right side as well. So they're going to fuse 15 and 17. So that's to do that. But if they do that, right, remember we move 15 down. So now there's a problem here. This is empty. Now 15 is empty. So what are they going to do? They're going to move 11 down. Okay, so now they move 11 down, which causes another underflow because now there's no root. Okay, so then now they're going to fuse 6 and 11 together. So they fuse 6 and 11 because they're siblings. So now once they fuse that, we have 5, 6, we have 6, 11 as the main root. We have 5, and then we have 8 and 10, and then 15 and 17. Okay, let's look at the performance of this. Yeah, this is the final tree. The performance, you can summarize the performance of the map as this. Height of 2 4 trees storing n entries is log of n. By proposition, a split transfer or fusion operation takes O of 1 time. A search, insertion, or removal of an entry visits log of n nodes. A size and empty is log O of 1. Find, insert, and erase is log of n. Performance of n entry map realized by a 2 4 tree. The space usage is O of n. Thus, the 2 4 tree provides for fast map search and update operations. 2 4 trees also have interesting relations to the data structure we discussed. Alright guys, now we're going to talk about red-black trees. So although AVL trees have a number of nice properties that have some map applications for which they are not well suited, for instance, the AVL tree may require restructure operations, rotations to be performed after each removal. The trees may require fusing or splitting operations to be performed after each insertion or removal. And the data structure we describe in this section, the red-black tree, does not have these drawbacks, but it does require that only O of 1 structure changes be made after an update in order to stay balanced. So what is a red-black tree? A red-black tree is a binary search tree with nodes colored red and black in a way that satisfies the properties. The root is black. So the main root is black. External property, every external node is black. So what does that mean? That means every single node that has no children is black, okay? Internal property, the children of every red node are black. Okay, so the children of every red node are black. Okay, so if you have a red node, the children of them are black. Depth property, all the external nodes have the same black depth. as in the number of black ancestors minus 1. Okay, wow, that's actually kind of really confusing. Okay, but whatever. So here we associate the 3, 2, 4 tree of 10.21. Okay, here's an example of red-black tree. It's not really suited that well because you can't really tell which is black and red. I'm guessing this is... Okay, so the root is black. We know this root is black, okay? Every external node is black. So all these... the node that has no children, okay, is black. Okay, so every external node that have no children. So all these, the nodes that have no children. So this has no children, so it's black. Wait, okay, are they portraying black as... No. Wait. I'm guessing, no, wait, this is not black. Wait, hold up. Is this even an example? I don't even think this is a red-black tree. Oh, whatever. Red-black tree says that each of the Dexter nodes has 4 black ancestors. 4 black ancestors. Hence, it has a depth of 3. We use the color blue instead of red. But wait, these are external nodes. Or are they talking about the, they're going to use null and say that those are the external nodes? Because this has no children. Okay, so they're using blue for representing red. Right, but here's the thing. Every external node is black, and this is an external node technically. This has no children. Yeah, this is black. This has no children, but why is this black? Why is this red? The children of red nodes are black. Okay, yeah, I know that, because this is red. So this children is black and black, okay? It's black. All the external nodes have the same black depth. Black ancestors minus 1. Okay, I kind of don't understand why how this is an external as red-black tree, but it doesn't matter. We use the color blue instead of red. Also, we use the convention of giving an edge of the tree have the same color as the child node. So as for the previous types of search trees, we assume that the entries are stored at the internal nodes of a red-black tree, with the external nodes being empty placeholders. Okay, yeah. Oh, okay, so they're saying... Okay, so these are... all the squares are the external nodes, and they're gonna say them as null. Is that what they're saying? We assume that the external nodes are actually real nodes. Okay, but we know that the extensive highly more external nodes could be null. Okay, so all the squares are null. Okay, so these are black. Okay, the squares are black. Okay, so those are the external nodes, and they're black because of every external node is black. The children of red nodes are black. So this is a red node, and these 2 children are black. Okay, that makes sense. Okay, so all the external nodes have the same black depth. Okay, I'm not subtracting 1 from the depth, but I'm not going to do that. But I'm guessing that's true. Okay, that makes more sense. Okay, so the external nodes, they're using squares for that. Oh, that's what they're doing. Okay, why don't they create like actual nodes for them? I don't understand that. But it doesn't matter. Okay, we can make the red-black tree definition more intuitive by having a correspondence between the red-black trees and the trees illustrated down below. Namely, given red-black tree, we construct a corresponding 2-4 tree by merging every red node V into a parent and storing the entry V at its parent. Conversely, we could transform any 2-4 tree into a corresponding red-black tree by coloring each node black and perform the following transformation for each internal node V. V is a 2 node, then we keep the black children of V as it is. If V is a 3 node, then we create a new red node W, giving V's first 2 black children to W, and make W and V's third children be the 2 children of V. If V is a 4 child node, then we create 2 new red nodes W and Z, give V's first 2 black children to W, give V's last 2 black children to Z, make W and Z be the 2 children of V. Okay, that's really complicated. Are they explaining this? Okay, so A you have 2 nodes, right? And they're gonna split that into, then keep the black children of V as it is. Okay, so then the black children are as it is. Okay, so A has 2 nodes, so you keep the black children as is. Okay, if V is a 3 node, yeah, so it has 3 nodes here. Create a new red node W, give the first two black children to W and make W and V's third child be the two children of the V. So give the first two black children. So you create a new node, you create a new red node. Okay. Red node. Okay, so we, in this case, 14. Give V's first two black children to W. First two black children. So first two black children. So this black children, we're gonna give it to 14, right? Give V's first two black children and make V and W and V's child to be the two children of V. So now 14 is gonna be the child of 13. That's what they're saying. Or you could vice versa do this way. If V is a 4-child node, then we create two new red nodes, W and Z. Okay, so V has 4 children, right? Create two new red nodes. Okay, 6. So yeah, W and Z. Give V's first two black children to W. So the first two black children, these two black children, they're gonna give it to W, which is 6. Give V's last two black children to Z. So these two last black children to Z, which is 8. And make W and Z be the two children of V. So now 6 and 8 become the children of 7. Okay, so that's what's going on. Okay. Okay, that's kind of complicated. A proposition, the height of a red-black tree is log of n. This is justification. I don't feel like reading that. You guys can read it. That's what it is. Okay. Okay, so we're gonna talk about update operations inserting into a in a red-black tree. My bad, red-black tree. Okay, so now consider insertion of the entry key with k keys into a red-black tree, keeping in mind their correspondence between the tree and its associated 2-4 tree prime, and the insertion algorithm for t prime. Algorithm initially proceeds as in a binary search tree. Namely, we search for the key in the tree until we reach an external node of t. When we say external, it means it has no children. We replace this node with the internal node z, storing the key and the key in x, and having two external node children. If z is the root of t, we color the z black. Else we color the z red. We also color the children with z black. This operation corresponds to inserting kx into the node of the 2-4 tree, t prime, with external children. In addition, this action preserves the root, external, and the depth properties of t, but it may violate the internal property. Indeed, if z is not the root of t and the parent v of z is red, then we have the parent and the child, namely v and z, that are both red. Note that by the root property, v cannot be the root of t, and by the internal property, which was previously satisfied, the parent u of v must be black, and since the wait, where was I on? My fault, complaint. Note that the root t v cannot be the root t, and by the internal property, the parent u must be black, but since z and its parents are red, but z's grandparents u are black, we call this violation internal property of the double red at node z. To remedy a double red, we consider two cases. Okay, case 1, the sibling w of v is black. In this case, the double red denotes the fact that we have created in our red-black tree t a malformed replacement for corresponding 4 node for the 2-4 tree t prime, which has its children, the 4 black children of u, v, and z. Our malformed replacement has one red node, v, that is the parent of another red node, z. Well, we want to have the 2 red nodes as siblings instead. To fix this problem, we perform a trinode restructuring of t. The trinode restructuring is done by the operations restructure, which consists of the following steps again. Take the node and the parent and the grandparent and label them A, B, and C, okay? In the left-right order, so that A, B, C will be visited in order traversal. Replace the grandparent u with the node labeled B, okay? And make nodes C, A, and C the children of B, keeping the in-order relationships unhinged. After performing the restructure, we color the B black, and we color A and C red. The restructure has this pattern. So we have Z. So here's the 4 configurations before restructuring. So this is a ZVU. What do they do? So what did they do? Made the U become, the grandparent become the child, right here. The child of, wait, okay, so first they made this become the right child of it, then they moved the down, then they, are these the same nodes? Okay, so now this, these two are red, right? And that's a grandparent. Make this the right child. So move V down. So now C has a value 20, V has a value 10, U is 30. Move 20 up. So now U has a value 10, V is 20, Z is 30. Move V down. Change the V to have value 30, Z to be 20, U to be 10. Then restructure it like that. I don't understand what they're doing. Take the node in its parents. I'm guessing it's the same thing as restructuring as the regular tri-node restructuring. I don't know. I don't think it even matters, to be honest. Okay, the case is sibling VW of V is red. In this case, the double red denotes overflow in the corresponding tree T. To fix this problem, we perform the equivalent of a split operation. We do the recoloring. Color V and W black and the parent U red. It's possible that after recoloring, the double red problem reappears, although higher up in the tree T. Since you may have a red parent if the double red problem reappears at U, then we repeat the consideration of the two cases at U. Thus, recoloring either eliminates the double red problem at node Z or propagates it to the grandparent U of Z. We continue going up T, perform recolorings until we finally resolve the double red problem with the number, thus the number of recolorings. Okay, log of n. Okay, so we have this, we split it. Okay, so Z has 10, V is 20, U is 30, W is 40. Before recoloring, and this is after recoloring. After the recoloring, and then they split. Wait, so they split. So now this becomes black. These two are black. This is red. Yeah, and this is still red. Okay. Okay, these are okay, so they insert 7, insert 12, recolor, move it. Insert 18, recolor, move this V down. So all the red became black, and this is still red. It's red, black, red. Holy crap. Okay. Restructuring causes a double red after recoloring. Okay. Initial tree, okay. I don't feel like reading it. Okay, the case of the insertion imply an interesting property for the red-black trees, namely since the case 1 eliminates the double red problem with the single tri-node restructuring. Case 2 action performs no restructuring operations. At most, one restructuring is needed in a red-black tree insertion. So by the above analysis and the fact that a restructuring or recoloring takes over 1, we have the following. The insertion of key into a rate chart can be a log of n, colorings in 1, tri-node restructuring. Okay. Well, let's talk about removal. So suppose we now have the ask to remove an entry K from the red-black tree. Removing such entry proceeds like a binary search tree. First, we search for a node U, storing such an entry. If node U does not have an external child, find the internal node V following U in the in-order traversal. Remove the entry V to U, perform the remove at V. Thus, we may consider only the removal of an entry with key K stored at a node V with the external child W. After we do this insertions, we keep in mind the corresponding between red-black trees and associated tree T prime. To remove the entry with KK from node V of T with the external child, we do as a proceeding. Let R be the sibling of W and X and be the parent of V. Remove the nodes V and W, make R the child of X. If V is red or R is red, hence W is black, we color R back. We are done. If instead R is black and V is black, then to preserve depth property, we give R a fictitious double black color. Now we have a double black color problem. Double black color delivers underflow. Okay, so there's it's a sibling of a UI or R has a child of Z. So in this case, we transfer operation in T prime. We perform a tri-node structuring by means of the operation restructure. Consider that the restructure takes the node Z, its parent Y, grandparent X, labels them temporarily left to right. A, B, C replaces X with the node label B, making it the parent of the other two. we color A and C black, give B the former color X and colors R black. This trinode restructuring element eliminates the double black problem, hence the most restructured performance removed in this case. Okay. Okay, way too much. The colors, okay, sibling colors, okay, so we do a recolor, we let color be color Y red. If X is red, we color it black. Hence after this, recoloring the double black color may be the problem errand of the R, that is, recoloring either eliminates the double black problem or propagates it into the parent of the current node. We then repeat a consideration of these three cases at the parent. Case 1 performs a trinode restructuring and stops in this number. The number of recoloring caused by removal is no or more than log n plus 1. Oh my gosh. Okay, this is really complicated. Okay, case 3. Y of R is red. Oh my gosh. In this case, we perform an adjustment operation as follows. If Y is the child of X, let Z be the right child of Y. Otherwise, Z is the left child of Y. Execute the trinode restructuring operation, restructure Z, which makes Y the parent of X. Color Y black, X red. Adjustment corresponds to choosing a different representation of a 3-node and 2-4 tree T prime. After adjustment operation, the sibling of R is black. Either case 1 or case 2 applies with a different meaning, X and Y. Note that if case 2 applies, a double black problem cannot reappear. Thus, to complete case 3, we have to make more applications, either case 1 and case 2 as being done. Okay, yeah. From the above argument, we see the updated method removes. Okay, so this is just an analysis. Okay, performance log of 1 log of n. Okay. Okay, now let's talk about the actual implementation, because that's the only thing that matters. Everything else we said before kind of doesn't really matter that much. Okay. Okay, so how do we implement a red-black tree? So we discussed, we're going to discuss how to implement a red-black tree. It is interesting to note that a C++ template library uses red-black tree in implementation for the map and multi-map. So technically the difference between the two is similar to the difference between our map and dictionaries ADTs. This STL map class does not allow entries duplicates, whereas multi-map does. However, in the behavior of the maps insert, our maps put function. If the key is not present, both function will insert a new entry. If the key is already present, the map ignores the request and the current map is unchanged. In contrast, our put method function replaces the existing value with the new value x. The implementation presented in this section allows for multiple keys. Present the major portions of the implementation in this section. To keep the presentation concise, we have omitted the implementations of a number of simpler utility functions. So we begin by presenting the enhanced entry class. RB entry is derived from the entry class code fragment 10.3. Inherits the key and value members and defines a member variable call. Stores the color of the node. Color is either red or black. It provides the member functions for us accessing and setting this value. These functions have been protected so users cannot access them. Okay, so we have the enumeration that has red, black. We have the color that make it friend so that our RB tree can access this RB entry. This type def just to make sure we have a better way to write key so that it's quicker. The color returns a color, is red, checks if it's red, but is black, checks is black, just sets the color, and the constructor just initializes it. Alright, that was pretty much that. So here now we have the definition of the red-black tree. The declaration is anonymous with the AVL tree, except that the utility function used to maintain the tree structure is different. We have present only the two most interesting utility functions, remedy double black and remedy double black. The meanings of the most two of the omitted entries are easy to infer, and it determines whether node V has the two external children. So now we have, this is going to inherit the search tree, and we're going to use the entry as the object for the search tree. So now we're going to have this type def is just a quick way to write iterator and stuff. All these type defs are just quick ways to write it. So you have the RB tree, the constructor. We insert out of position, remove the out of position, erase out of position. Remedy double red, remedy double black fixes the double red Z and the double red black R. So we invoke the insert a utility function of the search tree, which returns the position of the inserted node. If this node is the root of the search tree, we set the color black. Otherwise, we set it to color red and check whether the restructuring is needed to provide. Invoking remedy double black, double red. We perform necessary checks and restructuring present in the inserted code. Insert node. Z be the location of the newly inserted node. If both Z and its parents are red, we need to remedy the situation. To do so, we consider two cases. Let V be denote Z's parent and let W be V's sibling. If W is black, fall under case 1 of the insertion update procedure. We apply restructuring at Z. The top vertex of the resulting subtree V is set to black and the 2 children set to red. Okay, so here's an implementation. Insert into the base tree. If the root is always black, you set it black. Otherwise, rebalance, set a red, rebalance. Return the iterator to that position. Fix double red is how we do it. We get the position of the parent. If it's black, all okay. Return. Case 1, the sibling is black, then you got to restructure. And you set it black, then you set it with the left to be red, and then set the right to be red. Otherwise, case 2, recolor V, set it feed back to black. Set the sibling to black. Get the position of the parent. If the position of the parent is the root, make it red. If it's root, return. Otherwise, make it red, and then restructure. Yeah, that's what it is. Okay, now we talk about erase. If the iterator is an n, that means it's non-existent. We check if we erase u at the t position. You check if it's a root, if it's red, and if it was a parent red, then set it black, and then otherwise we restructure it. T position x parent, t position y sibling. Check is it black. If it is left is black, is right black. Gotta check if the save the top vertex color restructure y z x y z. Give z saved color. Set r black. Set the children black. Recolor r black and y black. Fix double black. Adjust grandchild of y's side restructure x, y, and z. Y is equal to black, x is equal to black. Fix r and k by case 1 and 2. Alright, that was pretty much red black trees. I think I kind of just breezed over it too quickly. Well, I'm really too tired. Anyway, rate, comment, subscribe. Maybe next time I'll actually pay attention and go over the depth of it more seriously. But yeah, rate, comment, subscribe. I'll check you guys later. Peace.